Okay, we're going to now look at lecture 5 on this vector algebra course. We're going to look at, let's see, the content says, the vector product a bit further, moments of forces, we've done that, area calculation, we've done that, rules, we've done that, Cartesian form. We're going to look at the triple vector product and some examples now. And then we're going to go on to look at vector equation of a line, which these dot product and vector product will inform us on. Okay, let's just quickly recap the vector or cross product, because we're going to be using that in this lecture. Now, if we've got two vectors A and B, we've got two vectors A and B, happy to be starting at the same point, but don't need to be, then A cross B is equal to the magnitude of A, magnitude of B, times by the sine of the angle between the two vectors, times a normal, a unit normal, so a vector that is normal to the plane that contains A and B. And it's a unit normal, so magnitude 1, so it doesn't actually change the size of this this sum, but it is a vector. So the result is a vector, because it's a vector product, in the direction at right angles to the plane that contains A and B. If we've done, so we can write the vector product or the cross product in component form, and we'll often expand it using this determinant form. We have ijk as the unit vectors, the three components of the two vectors A and B, and we write it as a determinant. Now, if you've done a determinant calculation before, when you did matrix algebra, and this is very straightforward and familiar. If you've not done matrices before, this won't be familiar and you need to just learn it. So this is the process of learning it. But you will be doing matrix algebra on this course anyway, so you will learn this determinant expansion. So we'll, in the rest of these lectures, assume that you know this determinant expansion to calculate the A cross B in component form. Just to remember that the A cross B in this vector form is exactly equivalent to this A cross B in component form. We have the three unit vectors in the direction of the axis systems, x, y, z, I, j, k, I squared, j squared, k squared are all equal to 0 because they're parallel. The angle between them is 0, so the sine of 0 is 0. So they're all 0. And because they're all at right angles to each other, I cross k is equal to I cross j is equal to k, j cross k is equal to I, and k cross I is equal to j. That's almost by the definition. And the anti-direction, so the opposite way around, we get the minus vectors, okay, because this is the cross product's dependent on the direction of the coordinate system. It needs to be right hand, so from x, y and z will point upwards. So remember them, they're quite handy to remember. You can look at the three axis systems and think about those, see whether you agree with those results. Cross product using Cartesian vectors. Well, let's just expand this out. We've got two Cartesian vectors. Well, we've got three terms in each bracket. We can expand those. It's quite a long expansion. We can expand it a bit more. But what we can see in this expression, we've got II, we've got JJ, we've got KJ. We know that they are 0, and we've got IJ, and we know it's K. So let's just substitute what we know. So we eliminate that. Let's have a look at a vector product calculation, fairly straightforward one. We've got three vectors, P, Q and R. We're asked to calculate P cross Q, P cross R and Q plus R. Well, P cross Q, we write the unit vectors and the three components of P and Q, and we expand them in the determinant way. I won't go into the detail. And then we do the expansion to get the three of the vectors. We do the same for P cross R. We can then look at, but the question doesn't ask us, is to add P plus Q and P plus P cross R, and we'll see that's 4 minus 10 minus 2. We're going to just do an expansion later. So Q plus R is straightforward, adding the components 2, 0, 4. Now if we were to expand P times Q plus R, we can do that. Get 4 minus 10 minus 2. And we saw that P cross Q plus P plus R is 4 minus 10, 2. So really just showing that you can expand the brackets for a cross product. It's multiplication. Cross product is distributive over addition. Right, we're going to look at the principle of transmissibility. This is something new. Now we know a cross product operation is used in 3D. Since the perpendicular distance, or the moment arm from the point O to the line of action, is not needed. So, as on this diagram here, the line across there, which would be a perpendicular distance, we never calculate. That's what this is saying. All we need to know is a point on the line through which the force acts. We never do the geometry of calculating the perpendicular distance, which you all know is what the force is. The moment due to the force is. So, how does this relate to the principle of transmissibility? So, in other words, we can use any position vector R. R can be this point, it can be lower here, as long as that point is on the line of action of the force. Okay. So we can write the moment, this M0 that we're trying to calculate, as F times R1 times R2 or times R3 crossed with R1, R2, R2, R3. Doesn't matter as long as R1, R2, R3 are on the same line through which F travels. And this idea is the principle of transmissibility. There's one further point of it, that F actually doesn't need to be in a single position. F can be further. F can be a vector. F is a vector along the line, whether it's here or whether it's here. It can be moving along there. So we can sometimes call it a sliding vector. But the whole thing that we can use different points, and F is a vector in any position, is the principle of transmissibility. Let's have a look at an example of using the principle of transmissibility. So we've got a particular example here. It's we can quite easily see what's happening. We've got a tractor pulling a rope that's attached to the top of a tree, 12 metres up a tree. It's offset about 4 metres on the ground, so we've got some geometry here. It's 12 metres along from the tree. Coordinate system's based at O. We know that the force that the tractor is pulling here is 2 kilonewtons, and we've got a line of action UAB. Okay. So determine the moment produced by the force F about the point O, about the bottom of the tree. let's draw the plane that that we're actually interested in here. So we can see that we could use either RA or RB to calculate the moment due to the force about O. So if we calculate RA using RA, or we just calculate RA in fact first of all, or RB, we calculate RB, we'll write it down in component form. Then the the force along of AB would be the unit vector along AB, which is just the vector divided by the magnitude of the vector times 2. And we can multiply this, which we can simplify that, and we can multiply this by, first of all, RA. So we need to do the cross product RA times FAB. And we see we get this. Again, needs expanding slightly. And we can do the same calculation with RB. I want to explain that one, which is the same as the calculation before. So MOX perpendicular to the plane containing both RA and RB. If we were to say, well, don't really trust that, let me calculate this moment being the force times the normal direction, well, we actually would be quite difficult to calculate that d distance. So it's a great benefit with vector calculations that we don't need to calculate this normal, the distance at right angles from the point of action to the line parallel to the plane, to the force. So we've got the vector product, 3 vectors, A cross B, A cross BC, A dot C times B minus B dot C times A. Remember, A dot C is going to give you a scalar. Solution 1. Well, we simply expand in the determinant form. You should get familiar to this. This vector is perpendicular to the plane containing AB. So the right angles to the plane containing B. It's normal to the plane containing AB. Yeah. Solution 2. A cross B cross C. So we've got A cross B, so that's second row, and C is this third. We expand that. This lies in a plane containing A and B. Is that understood? Solution 3, A dot C gives you a number, a scalar. B dot C gives you a scalar. 3 times B and 1 times minus 1 times A is what we have here. Gives you 3 minus 4, 2. And it's the same as A cross B cross A cross B cross C. And this is a standard result that not so obvious and sometimes useful to understand the relationship between the cross product and the dot product. We can always expand it the other way around as well, and it'll be the same. Let's have a look at an example here in the context of a hand pulling a wrench to undo a nut. So on a wheel. Now if we arrange the axis system so it's sticking out of at right angles to the wheel, find the moment of the force about the y-axis. Using vector analysis, we must first determine the moment of the force about O on the y-axis. So we have force. We know what that magnitude is. We have a position of the force by geometry. Let's work out what the moment is. We don't necessarily have the normal distance. So the moment's R cross B. The moment my along the x-axis is projection of m0 onto the y-axis and can be found by doing this dot product calculation, where j is a unit vector along the y-axis. And we can see this by looking at the planes involved here. Okay, we're going to generalise this approach to any axis with a unit vector UA. And the moment about the axis is MA dot MO. Remember that MO is R cross F. And we can write this moment in this determinant form and expand it, so we can do that determinant calculation. MA is the magnitude of MA times U. So let's just summarise this. The moment of force is the force times the perpendicular distance. You know that. That's your standard definition of a moment. In vector analysis, the moment about an axis is UA dot, the cross product of a point on the line of action of force. Any point. UA defines the direction of the axis, and R is any point, as I said. MA is calculated. If MA is calculated as a negative scalar, then the sense of direction of the moment is opposite to UA, opposite to the unit vector in the axis that we're calculating. The moment MA is expressed as a Cartesian vector is determined from MA UA. Let's do a calculation. Determine the moment MAB produced by the force in figure A. So we've got a force here acting on this shape, which tends to rotate the rod about the axis AB. So we want to find the moment of force about the axis AB. So we need a unit vector along AB. Then the component AB along AB is given by UAB times the moment of AB. So UAB dot R cross F, where R is any point on AB. So we can take the coordinates of B. For R, we'll work out the unit vector. UAB is that unit vector. Vector R is directed from any point on AB axis to the point to any point on the line of action of F is valid, but we use the vector. Position vector RC and RD are suitable, and we've shown them here. RA or RD, sorry, RC or RD. RC to me would be the most sensible, most obvious, because it's going through the point of action of the force and the centre of the coordinate system. BC are suitable, and RBD are suitable or valid. Choose the one which works for you. We're going to choose RD, so it's actually simpler to write. So the force then is is that vector in newtons. We need to calculate the moment along that axis, which is the dot times the cross of these two, which we expand as your determinant calculation. There's a lot of zeros in here, so it makes it a little bit easier. So the moment along AB is 80.5 Newton meters. This positive result indicates it's in the same sense of MB, in the same direction of UAB. And as a Cartesian vector, we can write this out as so. Let's do a calculation of area of a triangle now. 3 vectors defining the points P, Q and R. We need to work out P and Q. We need to work out P and R. So these are 3 sides of the triangle, or 2 sides of the triangle. We simply expand this determinant, and it comes out to be 3 minus 2 minus 1, but the area is half of that, this square root of that. 9 plus 4 plus 1 is root 14, divided by half. Let's look at the moment of a force about a point. Force of 6 units acts through the point P with these coordinates in the direction of 4, 1, 2. Find the moment of the force about the point Q. So we've got positions of points. We need to find PQ. We need to find a moment in the direction of the force. So we need to turn that force into a vector. So we do this here by getting a unit vector in the direction of the force. So 4, 1, 2. So the force vector is 6 times that 4, 1, 2. Position vector of P relative to Q is QP. So it's P minus Q. And the moment is simply QP cross with F. And we expand that. The units are units of distance times units of force. 5.4 in magnitude. Example of moment along an axis. So 2 forces act on the rod as shown in the figure. Determine the resultant moment they create about the flange. The flange is the connection to the wall at O, so the centre of the axis system. So determine the resultant moment they create about the flange, so about that point. So we need to create unit vectors and choose a position vector. Position vector directed from O to each of the to each force is shown in this lower figure, RA and RB. We can write those down. The resultant momentum about O is therefore the cross product of F times R and the cross product of F1 times RA and the cross product of F2 times RB. If F1 is that vector as given, F2 is that vector as given, then we simply cross product the two with your determinant expansions and add all the components. In this example, we've got a vector in pound-feet moment calculation, so American customer units. We've got this defined as the cosine vectors of the vector, so slightly different approach, but we can use this to define a vector. So we return to your direction cosine calculations. Okay, we'll now look at the triple product of vectors. There are two triple products of vectors. The triple vector product, the triple cross product, A cross B cross C, and the triple scalar product, A cross B dot C. A cross B creates a vector, so we can dot it with C. Triple scalar product is useful in geometrical meanings, like many of our vector calculations. We know that A cross B equals this, the area of a parallelogram. Remember that A and B is a vector, so we can calculate this this parallelogram area. It turns out we can get the volume of the expanded parallelogram, which we call a parallel piped. Okay, so it gives us the volume of a parallel pipe shape defined by three vectors, which is quite useful in geometry. So it follows that if only two vectors are parallel, you get a zero volume, because A cross B dot C is 0. If there are three vectors are coplanar, we get 0. If A cross B dot C is 0, then either A equals 0, B equals 0, or C equals 0. So there's three situations where we could get 0. Well, 5 situations if you like. 6 situations. 2 of the vectors are parallel. Okay, these are the same. They give the same volume of 0. So you need to check that we don't have any zeros or parallel vectors. Or indeed coplanar, 3 coplanar vectors. Just remember that you can expand the vectors multiply in slightly different ways. Let's do a quick calculation to demonstrate this. So I have 2 points AB, CD, AB, A to B is 2, 0, 1, because it's B minus A. A to C is C minus A. A to E is E minus A. So we can then work out the volume of that shape. We do the first cross product of AB cross AC, and we dot that with AE. Comes out to be 7 units cubed. Okay, if those coordinates were meters, this would be 7 meters cubed. Triple scalar product, and we've just seen, we can write it in these components as a determinant and expand that determinant as we would do normally. So example of a moment of a force. Determine the moment of the vertical 800 Newton force about point C. So 800 newtons acting down. What's the moment of this about point C? The force vector at A is 800 newtons down, so it's vertically down, so it's negative 800J. The position vector from A to C is C minus A. So minus CA, sorry. The moment is just RCA times the force vector, crossed with the force vector, which we can expand in the determinant. So we're going to look at this example of moments of force. We've got a plate, we've got three forces acting parallel to the y-axis. Here's the y-axis. We've got a 3 kilonewton one acting down, a 6 kilonewton one acting up, and a 2 kilonewton one acting down at the three corners at the dimensions shown here. The question is, determine the sum of the moments about the x-axis. So here's the x-axis. First thing we can see is that the 3 acts through the x-axis, so causes no moment. The perpendicular distance of the other two is 600 millimeters or 0.6 meters from the x-axis. So we can calculate our moment straight away from our normal rule. So F1, so if we call this 2 kilonewton one F1 acting down, causing say that's positive, and F2 6 newtons going up, we'll call that a negative. We get a positive and negative moment respectively. We multiply those together and sum them. We get 2.4 I kilonewton meters. And with the positive and negative is what we determine as being a positive from our definitions. We can do this calculation through vectors. So M1 be 0, 0.6 crossed with 0, minus 2, 0, the vector position, and that comes out to be 1.2I. Similarly, M2, this the 6 kilonewton vector comes out to minus 3.6, and well, we could look at the vector that we saw by inspection was 0. It comes out to be 0 because the distance of the second vector here is 0. We add the 3 and we get 2.4 as expected. Summary now, we've seen the vector product, moments of forces, area calculations, rules for vector product, Cartesian format, triple vector product, and latterly some examples.